Our universe is not a static picture, but a living story still being written. Throughout history, cosmic events have repeatedly shattered our understanding of reality itself. This video explores 30 of these pivotal moments, each one a discovery that fundamentally rewrote the rules of existence. You will learn how a single observation can overturn centuries of human thought. We will uncover why stars behave so strangely and what invisible forces truly control the cosmos. By the end, your perspective on space and time will be completely transformed. What part of the universe's story are you most curious to have rewritten before the 20th century? Many scientists pictured a universe that was eternal and unchanging. This comfortable view was shattered by the revolutionary idea of a cosmic genesis. The story begins not with a scientist, but a priest and physicist named Georges Lemaître. He proposed a staggering concept that the entire universe we see today, every galaxy and star, was once compressed into a single, unimaginably dense point he called the primeval atom. He suggested this point exploded, setting the cosmos into an expansion that continues to this day. To most astronomers, this sounded more like metaphysics than physics, a moment of creation that lay outside the bounds of traditional science. Then, an American astronomer named Edwin Hubble made a series of observations that turned the scientific world upside down. By studying the faint light from distant galaxies, Hubble noticed something peculiar. The light from almost every galaxy was shifted toward the red end of the spectrum. This redshift was a cosmic speedometer, indicating these galaxies were all racing away from us. More astonishing was the pattern. The farther away a galaxy was, the faster it appeared to be receding. The entire universe was not static, it was stretching, expanding in every direction, just as Lemaître's theory had predicted. The universe had a history, a story with a dramatic opening chapter. Yet the final, conclusive piece of evidence arrived by accident decades later. Two radio astronomers, Arno Penzias and Robert Wilson, were troubleshooting a persistent, faint hiss in their giant horn antenna. This annoying background noise was the same in every direction, day and night. They had stumbled upon the afterglow of the Big Bang itself, the cosmic microwave background radiation. This faint whisper of heat, cooled over billions of years to just a few degrees above absolute zero, was the cooled remnant of the universe's intensely hot and dense beginning. This discovery transformed the Big Bang from a radical hypothesis into the cornerstone of modern cosmology. It forced a profound philosophical shift. We no longer lived in an eternal, steady-state cosmos, but in a universe with a definite beginning, one that has been evolving and changing for nearly 14 billion years. This single event established the very fabric of space and time, setting into motion every cosmic drama that would follow. That faint hiss echoing from the dawn of time was far more than just background noise. It was a cosmic fossil, a snapshot of the universe in its infancy, captured when it was a mere 380,000 years old. Before that moment, the cosmos was a searing, opaque fog of particles and light. As it expanded and cooled, the first atoms formed, and the universe suddenly became transparent. That first burst of light, once brilliant, has been traveling for over 13 billion years, stretched and cooled by the expanding universe into the microwave whisper that Penzias and Wilson accidentally discovered. Their initial frustration with an unremitting signal they even blamed on pigeon droppings in their antenna was in fact the most important static in history. This uniform radiation field was the definitive evidence that tipped the scales, confirming the Big Bang theory over the competing idea of a steady-state universe. It proved our cosmos had a definitive hot beginning, but the story did not end there. Decades later, satellites like the Cosmic Background Explorer took even more precise measurements. They found that this cosmic microwave background is not perfectly smooth. It contains tiny, whisper-quiet variations in temperature, minute ripples that are the seeds of all cosmic structure. Those tiny fluctuations in the ancient heat map are the gravitational wells from which entire galaxies would eventually form. By studying this primordial blueprint, scientists could not only determine the universe's age with stunning accuracy, but also decode its fundamental composition, revealing the mysterious dark matter and dark energy that dominate it. This relic radiation continues to be one of our most valuable tools for understanding cosmic origins. It makes you wonder what other primordial signals from the birth of the universe are still out there, hiding in plain sight, waiting for a curious mind to tune into the right frequency. Those tiny ripples in the ancient light were a blueprint, but it took another leap to understand the blueprint was not fixed. It was stretching. The man who first saw this cosmic stretch was Edwin Hubble, working through cold nights at the Mount Wilson Observatory. His tool was the most powerful telescope of its era, the massive Hooker reflector, which he used to peer into the depths of space, measuring the faint glow of what were then called spiral nebulae. He confirmed these were not clouds within our own Milky Way, but entire island universes, galaxies in their own right, far beyond our own. But his most shocking discovery came from analyzing their light. He saw that the light from these distant galaxies was systematically shifted toward the red end of the spectrum. This redshift was a cosmic fingerprint, indicating that these galaxies were all racing away from our own. The universe was in motion on a scale no one had ever conceived. The farther out Hubble looked, the greater the redshift he measured. The more distant the galaxy, the faster it was receding. This simple, powerful relationship became known as Hubble's law. It proved the cosmos was not a static, unchanging backdrop as Einstein himself had once believed. Instead, the very fabric of space itself was expanding, carrying the galaxies along with it like raisins in a rising loaf of bread. This single observation provided the first direct observational evidence for the Big Bang, painting a picture of a universe that had a distinct starting point and had been growing ever since. By measuring the rate of this expansion, scientists could even run the cosmic film backward to estimate the universe's age for the very first time. This idea of an expanding cosmos forces us to confront profound questions about the nature of reality. If space is stretching, what is it expanding into, and what does this mean for the ultimate fate of everything we see? We are living inside an unfolding story, one where the stage itself is growing larger with every passing moment. How does it feel to live in a universe that is not just changing, but whose very dimensions are constantly evolving? This relentless expansion continues to shape not only the cosmos but our deepest understanding of our place within it. Yet this grand cosmic expansion was not the whole story. As astronomers mapped the motions of galaxies, they stumbled upon a profound mystery. The universe contained far more than what met the eye, a hidden architecture of gravity that defied all expectations. This discovery began in the 1930s with a brilliant and often contentious astronomer named Fritz Zwicky. He was studying the Coma Cluster, a vast collection of galaxies bound together by gravity. By measuring how fast these galaxies orbited the cluster's center, he could calculate the total mass required to hold them together. The result was staggering. The visible mass of all the stars and gas was only a tiny fraction of what was needed. The galaxies were moving so fast that they should have flown apart, scattering into the void. Zwicky proposed that some form of invisible matter, which he called dunkle materie, or dark matter, must be providing the missing gravitational glue. For decades, his idea was largely dismissed as an oddity. Then, decades later, astronomer Vera Rubin provided the undeniable evidence. With meticulous care, she mapped the rotation speeds of stars within spiral galaxies. According to Newton's laws, stars on the outer edges of a galaxy, far from the bright central mass, should orbit more slowly. Yet Rubin's data showed something astonishing. The stars at the edge were orbiting just as fast as those near the center. It was as if the entire galaxy was embedded within an enormous, invisible sphere of matter, its gravity pulling on the stars from all sides. The only explanation was that a vast halo of dark matter, completely unseen, was enveloping each galaxy. This mysterious substance does not interact with light at all. It does not shine, absorb, or reflect. We cannot see it, touch it, or contain it with any known material. Yet its gravitational influence is everywhere, sculpting the cosmos on the grandest scales. It acts as the cosmic scaffolding, the framework upon which galaxies formed and grew in the early universe. Without its relentless pull, the primordial gas from the Big Bang would never have clumped together to form the first stars and galaxies. We now know this dark matter makes up about 27% of the entire universe, while all the stars, planets, and nebulae we can see account for less than 5%. For decades, physicists have searched for what it actually is, hunting for hypothetical particles in deep underground labs and with powerful particle colliders. So far, it has eluded every direct detection. This leads to a haunting question. What if dark matter is not a particle in any sense we understand, but something even more alien, a manifestation of a flaw in our laws of gravity or a shadow from another dimension? This invisible component is a constant reminder that most of the cosmos is made of something we cannot perceive, challenging our most basic assumption that reality is composed of the stuff we can see and touch. This invisible cosmic scaffold of dark matter painted a picture of a universe destined to slow down. The immense gravitational pull of all that matter, both seen and unseen, was expected to act as a cosmic brake, gradually putting a drag on the expansion that began with the Big Bang. The only question for astronomers was whether that deceleration would be enough to eventually reverse the expansion, leading to a great crunch, or if the universe would simply coast toward a slow, cold halt. Then, in the late 1990s, two independent teams set out to measure this cosmic deceleration by using the universe's most reliable mile markers, a specific kind of stellar explosion known as a Type 1, a supernova. These supernovae occur in binary star systems when a dense white dwarf star siphons too much material from its companion, triggering a runaway thermonuclear explosion. Because these explosions always happen at the same critical mass, they shine with a remarkably consistent peak brightness. This makes them perfect standard candles, allowing astronomers to gauge their true distance with incredible precision. By measuring how bright these supernovae appeared from Earth, the teams could determine exactly how far away they were. They then measured the supernova's redshift to see how much the universe had stretched since the moment the explosion's light began its journey. They were looking for confirmation that the most distant and therefore ancient supernova were closer than expected, a clear sign that the universe was expanding more rapidly in the past and had since slowed down. Instead, they found the exact opposite. The distant supernova were fainter and thus farther away than anyone had predicted. The data pointed to a single, shocking conclusion. The expansion of the universe was not slowing down at all. It was speeding up. Some mysterious repulsive force, acting against the pull of gravity on the largest scales, was stretching the cosmos apart at an ever-increasing rate. This discovery was so revolutionary and so unexpected that the leaders of both research teams were awarded the Nobel Prize in Physics. The mysterious agent causing this acceleration was given a name: dark energy. We now understand that this enigmatic force makes up about 68% of the entire energy density of the cosmos, completely dominating its evolution and ultimate fate. It appears to be an intrinsic property of empty space itself, a constant energy density that grows more powerful as the universe expands and creates more volume. This revelation overturned centuries of scientific assumption and presented physicists with their most profound puzzle. How does knowing the universe will expand forever, growing colder and more isolated with each passing eon, reshape our perspective on cosmic destiny? It suggests a future where distant galaxies will one day fade from view, their light stretched beyond detection, leaving any far future astronomers in our own galaxy with a sky nearly empty of external wonders. The hunt to understand the true nature of dark energy, the force that governs this lonely future, continues to be one of the most urgent quests in all of science. For a century, Einstein's prediction of gravitational waves was a beautiful but unproven piece of his theory. These were not waves of water or sound, but actual ripples in the fabric of spacetime itself, caused by the most violent cosmic events. Their signal was expected to be so incredibly faint that Einstein himself doubted we could ever detect them. The quest to prove him wrong culminated on September 14, 2015, when the twin observatories of the Laser Interferometer Gravitational Wave Observatory, or LIGO, registered a signal that would change astronomy forever. For a mere 0.2 of a second, the lasers in detectors located in Louisiana and Washington state were jostled by a vibration smaller than the width of a single proton. That minuscule wobble was the unmistakable signature of spacetime itself ringing like a bell. The source was a cosmic collision that occurred 1.3 billion years ago, when two black holes, each dozens of times more massive than our Sun, spiraled into each other and merged. The energy released in their final moments was staggering, converting a mass equivalent to 3 entire suns into pure gravitational energy that rippled outward across the universe. This was not a discovery made with light, but with a new sense, allowing us to literally hear the universe for the first time. The signal was translated into a sound, a distinctive chirp that rose in frequency before ending abruptly, the final note of a billion-year-long dance. This single observation confirmed one of the last great predictions of general relativity and opened an entirely new window on the cosmos. We are no longer solely astronomers, we are now also cosmic listeners. This new sense has already revealed a hidden population of black holes, events that are completely dark to traditional telescopes. With each new detection, we are building a symphony of the cosmos, listening to the crashes and mergers that shape the universe. As our detectors grow more sensitive, what other cosmic events will we hear? Will we catch the faint whisper of a supernova's core collapsing, or the low hum from the dawn of time when the first black holes were born? This new era of multi-messenger astronomy, where we observe the cosmos through both light and gravitational waves, is revealing a reality far more dynamic and violent than we ever imagined. We are now tuning into the universe's deepest vibrations, listening to the very fabric of existence as it bends and warps. That faint cosmic whisper, the microwave background, holds a secret even deeper than its uniform temperature. Its incredible smoothness presented physicists with a profound puzzle. How could regions of the universe on opposite sides of the sky, which could not have exchanged information even at the speed of light, have reached the exact same temperature? This cosmic uniformity seemed impossible. The solution came in a radical new idea called cosmic inflation, proposed by physicist Alan Guth and others. This theory suggests that in the very first fraction of a second after the Big Bang, the universe underwent a breathtaking exponential growth spurt. For a fleeting moment, a patch of space smaller than a single proton expanded to a size larger than our entire observable universe. This incredible burst of expansion stretched the initial cosmos to perfect smoothness, ironing out any primordial wrinkles and explaining why the background radiation looks so uniform. But inflation did more than just smooth things out. It also amplified the tiny, random quantum fluctuations that are a fundamental part of reality at the smallest scales. Inflation stretched these microscopic vibrations to cosmic proportions, creating the faint ripples in density that we see imprinted in the cosmic microwave background. Those ripples were the gravitational seeds from which all cosmic structure would eventually grow, the blueprints for every galaxy, star, and planet in existence. Without this brief but monumental inflationary epoch, the universe might have remained a featureless, barren void. The most profound implication of inflation, however, is the suggestion of a multiverse. If this inflationary process could happen here, what is to stop it from happening elsewhere or even eternally? Our entire observable universe, with all its hundreds of billions of galaxies, may be just one isolated bubble in a vast, frothing cosmic ocean of other universes, each with its own unique physical laws and constants. Some of these bubble universes might have physics that allow for stars and life, while others might instantly collapse or remain forever empty. This idea forces us to confront a humbling possibility. The fundamental laws we are trying to decode may not be universal truths, but merely the local bylaws of our particular cosmic neighborhood. How would our search for meaning change if we confirmed our reality is just one accidental bubble in an infinite foam of other realities? While the evidence for inflation from the cosmic microwave background is strong, the hunt for direct proof, such as the faint signature of primordial gravitational waves from this explosive event, continues. Unlocking this secret would not just tell us how our universe began, but would reveal whether our cosmos is a unique event or one among a limitless and perhaps endless multitude. That idea of a multiverse presents a cosmos of infinite possibilities, but the real revolution was discovering that even our own universe is filled with other worlds. For centuries, the only planets we knew were the ones orbiting our own sun. The assumption was that our solar system might be a rare, if not unique, arrangement in a vast stellar emptiness. That assumption was permanently shattered in 1992 with the detection of the very first planets found beyond our solar system. The setting was not a sun-like star, but a pulsar, the rapidly spinning, super-dense corpse of a stellar explosion. The subtle wobble in the pulsar's clock-like radio signals revealed a system of at least 3 worlds orbiting this cosmic graveyard, proving that planets could form and survive in the most violent of environments. The true paradigm shift arrived 3 years later with the discovery of a planet orbiting a sun-like star called 51 Pegasi. This world, named 51 Pegasi b, was a giant, a Jupiter-sized behemoth. Yet it orbited so close to its star that its year lasted a mere 4 Earth days. This was a hot Jupiter, a type of planet that defied all our models of planetary formation. Its existence proved that other solar systems could be wildly different from our own, with planets in orbits and configurations no one had ever predicted. Suddenly, the galaxy felt both larger and more familiar, teeming with potential neighbors. The hunt for these exoplanets accelerated, but the field was truly revolutionized by a single mission, the Kepler Space Telescope. Instead of staring at one star at a time, Kepler fixed its gaze on a single patch of the Milky Way, continuously monitoring the brightness of over 150,000 stars. Its mission was to look for the telltale sign of a planet transiting or passing in front of its host star. When this happens, the star's light dims by a tiny, almost imperceptible fraction. Kepler's exquisite sensitivity allowed it to detect these minute winks of light. The data that came back was staggering. Kepler revealed that planets are not just common, they are the cosmic norm. On average, there are more planets in our galaxy than there are stars. It showed us that small, rocky worlds like Earth and Mars are incredibly abundant, with many residing in the habitable zone, that Goldilocks region around a star where temperatures could allow for liquid water to exist on a planet's surface. This single telescope transformed the search for life from philosophical speculation into a rigorous, data-driven science. We now know our galaxy is a tapestry of billions of worlds, each with its own story, its own landscape, and its own potential. The question is no longer if other Earths exist, but what we will learn when we finally point our next generation of telescopes at one and search its atmosphere for the chemical signatures of a living world. That moment will mark a turning point in human history, forever changing our understanding of life's place in the universe. Yet even as we mapped the cosmos on its grandest scales, a revolution was brewing in the microscopic realm, one that would challenge the very meaning of distance and separation. Albert Einstein, a pillar of modern physics, found one particular quantum idea so unsettling he famously labeled it spooky action at a distance. He was referring to quantum entanglement, a phenomenon where two particles become inextricably linked, their fates woven together. The spookiness emerges when you separate these particles, sending them flying to opposite ends of a lab, or even to opposite sides of the planet. The moment you measure a property of one particle, such as its spin, its distant partner instantly assumes a corresponding state. This connection appears to happen faster than the speed of light, seemingly violating a core principle of Einstein's own relativity. For decades, this was a philosophical debate, a troubling paradox in the mathematics. Then came the experiments. Scientists have now confirmed this quantum link over distances exceeding 1,000 kilometers, using satellites to send entangled photons between ground stations. The results are unequivocal. The particles are communicating, or rather coordinating, in a way that transcends our classical understanding of space. They behave not as two distinct objects, but as a single system, regardless of the physical miles between them. This has profound practical implications, forming the bedrock of emerging technologies like quantum computing, which promises to solve problems beyond the reach of any conventional machine, and quantum cryptography, which could create theoretically unbreakable codes. But the deepest implication is philosophical. Entanglement suggests that what we perceive as empty space and separate objects might be an illusion. At its most fundamental level, the universe may be deeply interconnected, a seamless whole where the concepts of here and there are not absolute. This forces a difficult choice. Either information can somehow bypass the cosmic speed limit, or our understanding of locality, the idea that objects are only influenced by their immediate surroundings, is fundamentally flawed. How does this microscopic interconnectedness reflect on our own experience of reality and consciousness? While the science does not support mystical links between human minds, it does hint that the fabric of the cosmos is woven from relationships, not just isolated things. We are left to wonder if the separateness we feel from the world around us is merely a feature of our large-scale, classical perception, while beneath the surface, the universe remains a single, entangled entity. For decades, black holes existed only as mathematical certainties and artistic renderings. They were the universe's ultimate ghosts, objects whose presence was felt only through their violent gravitational influence on their surroundings. We knew they were there, but we had never truly seen one. That all changed in April 2019, when the Event Horizon Telescope collaboration unveiled the first direct visual evidence. The target was a supermassive black hole at the heart of the galaxy Messier 87, a colossal entity weighing as much as 6.5 billion suns. To see something so small in the sky from such an immense distance required a telescope as large as the Earth itself. So scientists synchronized a global network of 8 radio observatories, from the high deserts of Chile to the volcanic peaks of Hawaii, creating a single planet-sized instrument. For several nights, these telescopes simultaneously stared at the same point in the void, collecting waves of light. The data they gathered was so vast it could not be sent over the internet. It had to be physically transported on half a ton of hard drives to central processing centers. There, supercomputers and algorithms painstakingly combined the signals, a process akin to assembling a cosmic jigsaw puzzle with pieces collected from around the world. The final image was a revelation, a fiery ring of orange and yellow light encircling a perfect sphere of darkness. This was not the black hole itself, for no light can escape it, but its shadow silhouetted against the incandescent whirlpool of its accretion disk. The superheated gas, spiraling inward at near light speed, glowed fiercely, tracing the contours of spacetime itself as it was dragged toward the point of no return. The size and shape of that dark central shadow matched the predictions of Einstein's general theory of relativity with stunning accuracy. It was a direct confirmation that we were looking at the event horizon, the one-way membrane where the known laws of physics break down. This single picture transformed black holes from theoretical phantoms into observable cosmic objects. It allowed scientists to test relativity in the most extreme gravitational environment imaginable, a place where time slows to a crawl and space is twisted into a vortex. We are now witnessing the violent dance of matter at the edge of infinity. What other cosmic illusions will be shattered as we train this global eye on other monsters, like the supermassive black hole at the center of our own Milky Way? Peering into these abysses does more than satisfy our curiosity. It forces us to question the very nature of reality in a place where space and time cease to have any meaning we recognize. The shadow of a black hole reveals a place of finality, but other stellar corpses spin with a rhythmic pulse that charts the cosmos. In 1967, a young graduate student named Jocelyn Bell Burnell was analyzing data from a new radio telescope when she noticed a peculiar, repeating signal. It was a series of sharp, precisely spaced pulses arriving every 1.337 seconds with unerring regularity. This was not the random crackle of stellar interference. It was a beat, a perfect cosmic metronome. The signal was so unnervingly artificial that Burnell and her supervisor half-jokingly labeled the source LGM1 for Little Green Men. The possibility, however remote, that they had stumbled upon a beacon from an advanced civilization was a thrilling and daunting prospect. The true explanation, when it came, was almost as strange. They had discovered the first known pulsar, a rapidly spinning neutron star. A neutron star is the unimaginably dense core left behind after a massive star explodes in a supernova. Squeezing more than the mass of our Sun into a sphere only about 12 miles across, a single teaspoon of its material would weigh billions of tons. As this stellar cinder spins, its intense magnetic field funnels beams of radiation from its magnetic poles. If these beams sweep across Earth's line of sight, like the lamp of a cosmic lighthouse, we observe a regular pulse of radio waves with every rotation. The discovery confirmed a wild theoretical prediction and revealed a new class of object where matter is crushed into a state that simply cannot exist on our planet. These pulsars are not just curiosities, they are the universe's most precise timekeepers. Their rotational periods are so stable that they rival atomic clocks. This incredible regularity has turned them into tools for cosmic navigation. The plaques aboard the Pioneer spacecraft and the golden records on the Voyager probes include pulsar maps, providing a way for any spacefaring civilization to locate our solar system based on the unique timing of these distant beacons. Pulsars have also provided some of the strongest tests for Einstein's general relativity. By observing a pair of pulsars orbiting one another, astronomers have watched their orbits slowly decay, exactly as predicted if they were losing energy by radiating gravitational waves. This was the first indirect but conclusive evidence that these space-time ripples were real, decades before LIGO made its first direct detection. These spinning stellar remnants are natural laboratories for physics under the most extreme conditions imaginable. What other secrets of fundamental forces will we uncover by listening to the steady, rhythmic ticking of these cosmic clocks as they mark the passage of time across the galaxy? That rhythmic ticking from a pulsar is a steady heartbeat, but the cosmos also sends us messages of pure, chaotic power. These messages arrive not as light or sound, but as silent, subatomic bullets. In the early 1900s, scientists were puzzled by the slow, steady discharge of electroscopes, instruments that measured electric charge. Even in a sealed container, the charge would gradually leak away, suggesting the air itself was being ionized by some mysterious, penetrating radiation. The assumption was that this radiation must be coming from the ground, a property of the Earth itself. A physicist named Victor Hess decided to take the investigation to the sky. He made a series of daring balloon flights, ascending to altitudes of over 5,000 meters, a perilous journey into the unknown at the time. He carried his electroscopes with him, and the data revealed a stunning reversal. Instead of decreasing with height, the ionization rate increased dramatically. The source of this radiation was not below, but above, pouring in from the depths of space. Hess had discovered cosmic rays, a constant, invisible rain of high-energy particles from the cosmos. We now know this cosmic rain is mostly protons and atomic nuclei, the building blocks of matter, accelerated to almost the speed of light. These are not mere particles, they are cosmic cannonballs. The most energetic cosmic rays detected carry a staggering amount of kinetic energy, comparable to a well-thrown baseball, all compressed into a single subatomic particle. This is an energy level millions of times greater than anything we can create in our most powerful particle accelerators, like the Large Hadron Collider. This fact alone presents a humbling question. What kind of natural particle accelerator exists out there that can achieve such phenomenal power? The origins of these ultra-high energy cosmic rays remain one of the greatest unsolved puzzles in astrophysics. They are too powerful to be trapped and steered by the Milky Way's magnetic fields, meaning they must come from relatively nearby in cosmic terms, yet we cannot pinpoint their source. Prime suspects are some of the most violent engines in the universe. An active galactic nucleus, where a supermassive black hole voraciously consumes matter, could generate immense shockwaves capable of flinging particles across intergalactic space. Others might be born in the cataclysmic fury of a gamma-ray burst, the death cry of a massive star. Because these particles are charged, their paths are bent and scrambled by magnetic fields as they travel, erasing any clear trail back to their origin. They are messengers that arrive without a return address, carrying the news of a distant cataclysm but refusing to reveal its location. By studying their composition and energy, we gain a unique window into the most extreme processes in the universe, events that are often invisible to our telescopes. Every second, thousands of these cosmic messengers pass straight through our bodies and our planet, a silent testament to the universe's relentless, high-energy violence. What other secrets about the most powerful explosions in creation will we unlock by learning to read these cryptic, high-speed letters from the void? Those silent cosmic bullets are not the only high-energy messages from the void. In the 1950s, radio astronomers began cataloging strange, powerful signals that seemed to emanate from points in the sky with no visible counterpart. These radio sources were given dry catalog names, but their nature was a complete enigma. They were not stars, and they were not ordinary galaxies. The mystery deepened in 1963 when astronomer Martin Schmidt was studying one of the most perplexing of these objects, known as 3C273. He was trying to decipher its strange light signature, which contained emission lines that did not match any known chemical element. After months of frustration, he had a sudden, brilliant insight. The pattern was not unfamiliar, it was simply shifted. The lines were the well-known signature of hydrogen, but they had been stretched or redshifted to an astonishing degree. This single realization cracked the code. 3C273 was not a nearby star. It was an object fleeing from us at nearly 15% the speed of light, located billions of light-years away. They named this new class of object a quasar, a portmanteau of quasi-stellar radio source. The immense distance meant these quasars were not just bright, they were unthinkably luminous, outshining our entire Milky Way galaxy by a factor of 1,000. All from a region smaller than our own solar system. The question was, what cosmic engine could possibly generate such staggering power from such a tiny volume? The only conceivable answer was a supermassive black hole, a gravitational monster weighing billions of times the mass of our Sun. A quasar is the visible, screaming signature of such a black hole in its most active, violent phase. Vast clouds of gas and even entire stars are torn apart by the immense tidal forces, their material forming a searingly hot accretion disk as it spirals toward the event horizon. The friction within this whirling maelstrom heats the gas to millions of degrees, causing it to glow with an intensity that can be seen across the universe. In this extreme environment, gravitational energy is converted directly into a flood of radiation with breathtaking efficiency. Quasars are not just distant curiosities, they are cosmic lighthouses that allow us to peer back to the universe's infancy. The light from the most distant quasars has been traveling for over 13 billion years, showing us a time when galaxies were first assembling. This presents a profound puzzle for cosmologists. How did these billion solar mass black holes form so quickly after the Big Bang? Their very existence so early in cosmic history challenges our models of how structure grows in the universe, suggesting that the seeds for these giants must have been planted in the very first moments. Today, most quasars have fallen silent as their fuel supply was consumed, and the supermassive black holes at the centers of galaxies, including our own, now lie mostly dormant. We are left to wonder, was our Milky Way once a brilliant quasar, its central heart blazing across the cosmos? And if so, what cosmic event finally switched off its incredible light? Those quantum seeds planted during inflation needed a force to nurture them into galaxies. That force was gravity, the universe's master architect. Over billions of years, the slight over densities in the primordial soup, those tiny ripples in the cosmic microwave background, began to pull in more and more matter. Dark matter, with its relentless gravitational pull, formed an invisible scaffolding first, creating vast gravitational wells. Ordinary matter, the gas that would become stars, then flowed along these dark matter filaments, pooling at the intersections like water converging in a river delta. The result is the largest structure we know of, the cosmic web. This is not a random scattering of galaxies, but a magnificent, interconnected network of brilliant galaxy clusters strung along gossamer threads of dark matter, separated by unimaginably vast, dark, and nearly empty cosmic voids. These voids are so large that if our Milky Way were placed in the center of one, we would see almost nothing in the sky, a profound and lonely darkness. We can now simulate this entire process from the first moments after the Big Bang to the present day, using some of the world's most powerful supercomputers. These virtual universes, when their parameters are set to match our observations of dark matter and dark energy, produce a distribution of galaxies that is a near-perfect match to what our telescopes actually see. This is a staggering achievement, a confirmation that we truly understand the broad strokes of cosmic evolution. The precise pattern of this cosmic web, the thickness of its filaments and the size of its voids, acts as a cosmic scale, precisely weighing the universe's ingredients. It tells us, independently of any other measurement, exactly how much dark matter and dark energy exists. This grand structure connects scales in a way that is almost incomprehensible. The entire luminous universe, with all its hundreds of billions of galaxies, is the grown-up version of quantum mechanical vibrations, microscopic randomness stretched to a cosmic canvas and given form by gravity. This means that the specific location of our own Milky Way galaxy, on a spur of one filament in a modest galactic cluster, can be traced back to a particular infinitesimal fluctuation in the first fraction of a second of time. Our cosmic address was written by quantum probability. How does it feel to know that the grandest structures in existence are the amplified echoes of the very smallest, and that this growth from quantum seed to cosmic forest is a process that continues silently and magnificently all around us? The grand cosmic web is built on gravity, but another, more elusive particle flows through its vast expanses almost entirely unnoticed. These are neutrinos, the universe's ghost particles. Their story begins not with a telescope but with a theoretical puzzle. In the 1930s, physicist Wolfgang Pauli was troubled by a seeming violation of a sacred law of physics, the conservation of energy. During a type of radioactive decay known as beta decay, a tiny amount of energy always went missing. Pauli proposed a radical solution, a new, invisible particle that was carrying the missing energy away. He was so convinced his idea was untestable that he famously said, "I have done a terrible thing. I have postulated a particle that cannot be detected." He called it a neutron, a name later given to a different particle, while his ghostly candidate became the neutrino. For decades, it remained just a line in an equation, a mathematical fix for a cosmic accounting error. The hunt to prove its existence fell to physicists Clyde Cowan and Frederick Reionization. Their plan was audacious: to catch the fleeting flash of a neutrino interacting with matter. They built their detector near a powerful nuclear reactor, a prolific artificial source of these particles. The signal they were looking for was incredibly rare, as neutrinos barely interact with anything. Trillions pass through your fingertip every second, leaving no trace. In 1956, after a painstaking search, they saw the unmistakable signature, a double flash of light caused by a neutrino colliding with a proton. They had done the impossible. They had caught a ghost. This confirmed that neutrinos are real and are produced in staggering numbers by nuclear reactions. The Sun, a giant nuclear furnace, bathes Earth in a constant, silent torrent of solar neutrinos. Yet when scientists first tried to count them, they hit a wall. They were detecting only about 1/3 of the number predicted by our best models of the solar core. This was the solar neutrino problem, a mystery that persisted for decades. The solution was as strange as the particles themselves. We now know that neutrinos are not one, but three distinct types: the electron neutrino, the muon neutrino, and the tau neutrino. And as they travel through space, they do not hold their identity. They oscillate, morphing from one type to another in a constant, silent dance. The early detectors were only sensitive to one type, the electron neutrino, and were missing the others that had changed along the journey from the Sun. This discovery of neutrino oscillation was monumental. It proved that these particles, long thought to be massless, must have a tiny amount of mass. This was a fundamental breakthrough that forced physicists to revise the standard model of particle physics. Today, immense observatories buried deep underground in Antarctic ice or at the bottom of the sea watch for the rare flashes of these cosmic phantoms. They are our only direct window into the heart of a living star, allowing us to see the nuclear fusion happening in the Sun's core in real time. When a star explodes as a supernova, 99% of its colossal energy is released not in light, but in a tremendous burst of neutrinos, a ghostly shockwave that arrives hours before the light of the explosion. These messengers from the most violent events carry information that light cannot, traveling straight from their source without being deflected by magnetic fields or absorbed by cosmic dust. They are the perfect cosmic couriers. What will we learn when the next nearby star goes supernova and our detectors are flooded with its neutrino story, a narrative of stellar death written in particles that barely exist? The universe's ghost particles slip through matter unnoticed, but its most violent explosions announce themselves with a scream of pure energy. In the late 1960s, American military satellites designed to monitor secret nuclear weapons tests began picking up brief, intense bursts of gamma radiation. These flashes were not coming from Earth but from deep space. For decades, their origin was one of astronomy's most guarded secrets, a cosmic puzzle born from Cold War surveillance. The data was eventually declassified, revealing a sky punctuated by these random, unimaginably powerful events, each one a gamma-ray burst. For a few seconds, these bursts can outshine every star in 100 billion galaxies combined, making them the most luminous electromagnetic events known to exist in the cosmos. The energy released is staggering, more than our Sun will emit across its entire 10 billion-year lifespan, all concentrated into a fleeting flash. The mystery was so profound that theories ranged from alien starships exploding to the final death rattles of comets falling into distant black holes. The breakthrough came when more advanced satellites could pinpoint the locations of these bursts and observe their fading afterglow at other wavelengths. This revealed that they were occurring in galaxies billions of light-years away, confirming their almost incomprehensible power. We now understand there are two primary types of these cosmic cataclysms. Long-duration gamma-ray bursts lasting more than 2 seconds are thought to be the birth cries of new black holes. They occur when a rapidly spinning, massive star, dozens of times heavier than our Sun, exhausts its nuclear fuel and collapses. As its core implodes into a black hole, powerful jets of material are blasted outward at nearly the speed of light. If one of these ultra-relativistic jets is pointed directly at Earth, we see the brilliant, focused beam of a gamma-ray burst. The shorter bursts, lasting less than 2 seconds, had a more elusive origin until a historic event in August 2017. Gravitational wave observatories detected the ripples from 2 neutron stars colliding. Just 2 seconds later, telescopes in space saw a gamma-ray burst coming from the same patch of sky. This was the smoking gun, the first confirmed multi-messenger observation of a cosmic event. The collision of these two incredibly dense stellar corpses created a spectacular fireworks show, forging heavy elements like gold and platinum and scattering them across the cosmos. The very gold in a wedding ring was likely forged in such a violent merger billions of years ago. Yet the fundamental physics behind these engines remains a frontier of research. How can a stellar collapse or a neutron star merger focus and accelerate particles to such phenomenal energies, creating a beacon visible across the universe? The random nature of these events is both humbling and unsettling, a reminder that the cosmos is capable of producing sudden, planet-sterilizing flashes of radiation without warning. What would it mean for life in a galaxy if one of these cosmic guns were to fire a jet in our direction? And how many civilizations might have had their stories cut short by such a random, titanic event? The gold forged in a stellar collision is a testament to deep time, but how do we measure that time itself? The universe's age is not a guess, but a conclusion drawn from multiple, independent cosmic clocks, all ticking in remarkable agreement. The most direct method comes from tracing the expansion backward. By precisely measuring how fast galaxies are receding from us today, a value known as the Hubble constant, we can rewind the cosmic film to the moment when everything was compressed into a single point. This calculation points to an age of roughly 13.8 billion years. A second, completely different line of evidence comes from the oldest objects we can observe. In the halos of our own Milky Way, astronomers have identified ancient stars, their atmospheres almost entirely devoid of heavy elements forged in earlier stellar generations. By analyzing their light, we can determine their composition and place them on stellar life cycle charts, revealing stars that are over 13 billion years old. The universe, of course, must be older than the oldest stars within it. The most precise clock of all, however, is the cosmic microwave background. The detailed pattern of its faint temperature ripples, imprinted when the universe was a mere infant, acts as a cosmic fingerprint. By analyzing the exact size and distribution of these ripples, scientists can calculate the universe's fundamental ingredients, the amounts of ordinary matter, dark matter, and dark energy, with exquisite precision. Plugging these values into our cosmological models yields a definitive age, 13.77 billion years, with an uncertainty of just 40 million years. That these three completely independent methods, the expansion rate, the oldest stars, and the primordial afterglow, all converge on the same number is a stunning triumph of modern science. It gives us immense confidence that our broad brush story of the cosmos is correct. This timeline is not just a number, it is a narrative. It tells us that the first stars ignited a few 100 million years after the Big Bang, ending the cosmic dark ages. It reveals that galaxies began to assemble soon after, and that our own solar system is a relative newcomer, forming when the universe was already about 9 billion years old. This cosmic chronology places our existence in profound perspective. If the entire history of the universe were compressed into a single calendar year, with the Big Bang at the stroke of midnight on January 1st, all of recorded human history would occupy less than the final second of December 31st. We are living in the universe's mature years, long after its fiery birth and its wild, formative epochs. How does it feel to know that we are the latecomers, the product of nearly 14 billion years of cosmic evolution, arriving just in time to look back and begin to understand the story? That ghostly neutrino rain from the sun held a secret for decades, a cosmic accounting error that baffled physicists. Our most trusted models of the solar core predicted a specific number of electron neutrinos should be arriving on Earth, a direct count of the nuclear fusion powering our star. Yet when scientists built massive, deep underground detectors to tally them, they consistently came up short, finding only about 1/3 of the expected number. Where were the missing neutrinos? This was the solar neutrino problem, a glaring discrepancy that suggested either our understanding of the sun's inner workings was fundamentally wrong, or something strange was happening to the neutrinos on their journey. The solution, when it finally came, was more fantastic than anyone had imagined. It was not that the models were wrong, it was that the neutrinos themselves were changing. We now know there are three distinct types or flavors of neutrinos. The Sun produces only electron neutrinos in its core, but as these ghostly particles travel through space, they do not hold their identity. They oscillate, spontaneously morphing between the electron, muon, and tau types in a constant, silent dance. The early detectors were only sensitive to the original electron neutrino, completely missing the two-thirds that had transformed along the way. This discovery of neutrino oscillation was revolutionary. It proved that these particles, long assumed to be completely massless like photons, must have a tiny but non-zero mass. This was a monumental crack in the otherwise incredibly successful standard model of particle physics, forcing physicists to revise their most fundamental theories of the subatomic world. The confirmation came from a new generation of exquisite experiments, the Super Kamiok and detector in Japan, a colossal tank filled with 50,000 tons of ultra-pure water surrounded by sensitive light sensors, watched for the faint flashes created by neutrino interactions. Then the Sudbury Neutrino Observatory in Canada, using heavy water, provided the definitive proof by demonstrating its ability to detect all three neutrino flavors, finally accounting for 100% of the Sun's predicted output. This resolution did more than just solve a puzzle. It wove together the physics of the impossibly large and the infinitesimally small. We can now use neutrinos as a direct probe into the heart of a star, confirming our models of stellar fusion with a certainty that light alone could never provide. This subtle particle transformation hints at a deeper symmetry woven into the fabric of reality, a hidden layer of complexity in the most elusive particles we know. It makes you wonder what other cosmic messengers are changing their identities on the way to us, and what secrets about the universe's fundamental rules are they trying to tell us. The vastness of space is not something we can measure with a single cosmic ruler. To map the cosmos, astronomers built a ladder, a series of interlocking steps where each new method relies on the one below it. This cosmic distance ladder begins at our own front door with radar ranging, bouncing radio waves off nearby planets to lock in the precise scale of our solar system. This foundational step then calibrates the next stellar parallax, which measures the tiny, apparent shift in a star's position as Earth orbits the Sun. It is like holding a finger out and closing one eye, then the other, watching it jump against the background. That tiny jump, when measured with exquisite precision, gives us the distance to our stellar neighbors. But parallax fades into imperceptibility beyond a few thousand light-years. To reach further, we needed a new kind of rung, a standard candle. These are celestial objects with a known intrinsic brightness. By comparing how bright they appear from Earth to how bright they truly are, we can calculate their distance with remarkable accuracy. The most famous of these are Cepheid variable stars, pulsating giants whose pulse rate is directly tied to their true luminosity. A slower, grander pulse means a brighter star. Edwin Hubble used these cosmic beacons to settle a great debate, identifying Cepheids in the Andromeda Nebula and proving it was not a cloud within our own galaxy, but an entire island universe millions of light-years away. This single measurement instantly expanded the known universe, revealing a cosmos filled with galaxies. To reach the farthest horizons, we need the brightest standard candles, the Type 1, a supernova. These stellar explosions always occur at the same critical mass, so they always shine with the same peak brightness, outshining entire galaxies and making them visible across billions of light-years. It was by carefully measuring the apparent dimness of these distant supernovae that astronomers made the shocking discovery of dark energy. Each rung of this ladder is carefully cemented to the one below, creating a chain of measurement that stretches from our backyard to the edge of the observable universe. This stepwise approach to cosmic cartography has done more than just give us numbers. It has given us a profound sense of scale, transforming the night sky from a flat canopy of anonymous lights into a three-dimensional volume with depth, history, and staggering immensity. How does it feel to know that our entire understanding of the cosmos, from its age to its accelerating expansion, rests upon this carefully constructed staircase of light, a human invention that allows us to measure infinity itself? That cosmic web, a vast network of galaxies, holds a subtle rhythm woven into its very structure. Long before the first stars ignited, the infant universe was a seething, opaque sea of particles and radiation. In this primordial soup, gravity would try to pull matter together into clumps, but the intense pressure from the radiation bath would push it back out. This created a cosmic tug-of-war, generating powerful sound waves that raced outward at over half the speed of light. These were not sound waves as we know them, but spherical pressure fronts propagating through the superheated plasma. Then, when the universe was just 380,000 years old, it cooled enough for atoms to form in an event called recombination. The radiation, suddenly freed, streamed away as the cosmic microwave background, and the matter, released from the pressure of the light, froze in place. The sound waves stopped dead in their tracks, imprinting a faint, spherical shell of slightly denser matter around every initial fluctuation. This fossilized echo is known as a Baryon acoustic oscillation. It created a preferred scale, a standard ruler etched into the cosmos. Today, that same scale is visible as a subtle statistical preference for galaxies to be separated by a specific distance, about 500 million light-years. By conducting massive galaxy surveys that map the three-dimensional positions of millions of galaxies, astronomers can measure this characteristic scale. Because we know its true size from the physics of the early universe, we can use it as a cosmic tape measure. By seeing how this ruler appears stretched or compressed at different cosmic epochs, we can trace the expansion history of the universe with extraordinary precision. This provides an independent and powerful confirmation of dark energy, revealing how its repulsive force has influenced the stretching of space over billions of years. These frozen sound waves connect the universe's first moments to its present-day architecture, tying the microscopic physics of a hot, dense plasma directly to the grand cosmic web we observe. It is a direct link between the largest structures and the earliest times. What other primordial rhythms might be hidden within the distribution of matter, waiting for a sophisticated enough map to reveal their silent, cosmic music? Those invisible threads of magnetism weave through the cosmos on a scale we are only beginning to fathom. We often think of magnetic fields as belonging to planets or stars, but they also stretch across the vast emptiness between them, a ghostly web of force that permeates entire galaxies and even the space between them. These cosmic magnetic fields are unimaginably weak, millions of times fainter than the pull of a common refrigerator magnet. Yet across light years of emptiness, their influence becomes profound. We cannot see them directly, but we can read their signatures in the light that passes through them. When starlight travels through a magnetized region of space, its waves become polarized, all aligning in a specific direction like sunlight glinting off the surface of a lake. By studying this polarized light, astronomers can map the invisible magnetic architecture of our galaxy. Another telltale sign is a phenomenon called synchrotron radiation, a faint, distinctive glow produced when high-energy electrons, often accelerated by supernova remnants, spiral along the lines of a magnetic field at nearly the speed of light. This eerie light paints the magnetic fields of distant galaxies in radio waves, revealing their intricate shapes. The true mystery lies in their origin. How did such vast magnetic structures come to be? One possibility is a cosmic dynamo, where the rotation of a galaxy's conductive gas and plasma over billions of years can amplify a tiny initial seed field into the large-scale structures we observe. Another, more profound idea is that these magnetic seeds were sown in the very early universe, perhaps during the inflationary epoch or the phase transitions that followed the Big Bang. Once established, these fields become cosmic architects. They guide the flow of interstellar gas, channeling material along invisible highways and helping vast clouds collapse to form new stars. They influence the structure of spiral galaxies, shaping their majestic arms. They even act as a galactic maze for cosmic rays, those high-energy particles from distant explosions, bending their paths and making their origins so difficult to trace. Without these pervasive magnetic forces, galaxies would look and evolve in dramatically different ways. The universe is not just held together by gravity, but also sculpted by this invisible, pervasive magnetism. How did such a subtle force become woven into the fabric of the cosmos? And what does its silent, persistent pull tell us about the hidden dynamics that govern the birth and life of every galaxy? The idea of a multiverse transforms the cosmic story from a single narrative into a library of infinite possibilities. This radical framework suggests that our universe, with its hundreds of billions of galaxies, might be just one bubble in a frothing cosmic ocean of other universes, each with its own unique physical laws. This concept is not pure science fiction. It emerges as a natural and perhaps unavoidable consequence of several of our most successful physical theories. The inflationary model of the Big Bang, for instance, suggests that the rapid expansion of our early universe could be an eternal process, continuously spawning new bubble universes in an endless cosmic foam. String theory, an attempt to unify all fundamental forces, mathematically allows for a staggering number of possible vacuum states, each one representing a different universe with different constants and particles. Even the strange rules of quantum mechanics, with their inherent probabilities, hint at a reality where every possible outcome of an event actually occurs, branching off into its own separate world. The profound implication is that the laws of physics we are trying to decode may not be fundamental truths at all, but merely the local bylaws of our particular cosmic neighborhood. This provides a potential and deeply humbling explanation for the apparent fine-tuning of our universe for life. If the fundamental constants, like the strength of gravity or the mass of an electron, were even slightly different, atoms and stars could never have formed. The multiverse idea suggests we do not live in a specially designed cosmos. We simply inhabit one of the rare universes where the numbers, by pure chance, happen to allow for our existence. This pushes the very definition of science to its limits, as these other universes may lie permanently beyond our observational reach, raising the question of whether an untestable idea can still be considered scientific. How would confirming we live in a multiverse transform our perspective on reality? It would mean that every cosmic story we can imagine, and countless more beyond our imagination, are all unfolding somewhere in the vastness of the metacosmos. This expansive concept continues to challenge our deepest assumptions, forcing us to wonder if the ultimate nature of reality is not a single set of rules, but an endless tapestry of variation. Einstein's theory was a beautiful mathematical tapestry, but its most personal prediction seemed almost magical, that time itself could stretch and slow. The confirmation came not from a distant star, but from a pair of precisely engineered clocks. In one of the most famous experiments in modern physics, scientists placed incredibly accurate atomic clocks aboard commercial airplanes flying around the world. After the journeys, they compared these clocks to identical ones that had remained stationary on the ground. The result was a tiny but undeniable difference, a fraction of a second gained by the traveling clocks. Time had literally passed faster for the clocks in the air, just as relativity predicted. This was not a flaw in the mechanisms, it was the universe's own clockwork, proving that velocity alone can alter the passage of time. An even more extreme example rains down on us constantly from the upper atmosphere. Muons, subatomic particles created when cosmic rays strike the air, are so unstable that they should decay into other particles after traveling only a few hundred meters. Yet we detect them in abundance at sea level. How is this possible? From our perspective on the ground, time for these muons hurtling toward us at nearly the speed of light is stretched out dramatically. Their internal clocks tick so slowly that their fleeting lifespan is extended just long enough for them to complete the journey to Earth's surface. The most ubiquitous proof, however, is in your pocket. The Global Positioning System is a constellation of satellites, each carrying an atomic clock. These satellites orbit at high velocity, which slows their time relative to the ground, but they are also higher in Earth's gravitational field, which speeds time up. The net effect is that their clocks run faster by about 38 millionths of a second per day. If the system's computers did not constantly correct for this relativistic drift, the GPS coordinates on your phone would become inaccurate by several miles within just a few hours. Our daily navigation depends entirely on acknowledging that time is not absolute. This temporal flexibility forces a profound shift in perspective. The universal now is an illusion. Your moment and the moment of someone on a distant planet are not the same. The flow of reality is not a single river, but a vast delta of countless streams, each moving at its own pace. How does it feel to know that your very movement through space is quietly shaping your journey through time, and that every second you experience is uniquely your own? The cosmic web is not just a structure of light, but also one of profound emptiness. Between the brilliant filaments and clusters of galaxies lie staggering voids, regions of space so empty they defy easy comprehension. These are not small pockets of nothing, but cosmic deserts spanning hundreds of millions of light years. The most famous of these, the Boötes Void, was identified in the early 1980s. It is a spherical region of space roughly 330 million light-years across. If our Milky Way galaxy were at its center, we would not have known other galaxies existed until the 1960s. In a volume of space that should contain thousands of brilliant galaxies, astronomers have found only a handful. This is not a mere gap, it is a staggering absence. The existence of such voids forced a dramatic revision of our cosmic map. The universe is not a uniform soup, but a sponge-like structure of dense clusters and vast, nearly vacant bubbles. These voids are natural laboratories for studying dark energy. With so little matter inside them to provide gravitational pull, the repulsive force of dark energy operates almost unopposed, causing these empty regions to expand even faster than the more crowded parts of the universe. They are the clearest windows we have into the behavior of this mysterious energy that dominates our cosmic fate. How did such immense nothingness come to be? The leading theory suggests they are the grown-up versions of the tiniest under-densities in the primordial universe. While gravity was pulling matter together into the knots that became galaxy clusters, it was simultaneously draining matter away from these regions, leaving behind ever-growing empty bubbles. The sheer scale of these voids tells us that the initial conditions of the universe had a much wider range of fluctuations than we once thought. Their existence challenges the cosmological principle, the long-held assumption that on the largest scales, the universe is smooth and homogeneous. We now see a cosmos of dramatic contrast, a tapestry woven with threads of brilliant light and expanses of deep, silent shadow. What does it mean for our place in the cosmos that we live not in a vast, average region, but in a relatively dense neighborhood, a bright oasis surrounded by an immensity of near-nothingness? That profound emptiness of the cosmic voids was not the universe's original state. For hundreds of millions of years after the Big Bang, the cosmos was simply dark, a featureless expanse of neutral hydrogen gas. This was the cosmic dark ages, a time when no stars existed to pierce the gloom. Then a revolution began. The first generation of stars ignited, and their brilliant ultraviolet light began to tear through the primordial fog. This was the epoch of reionization, a universal transformation that fundamentally altered the cosmos. The intense radiation from these first, incredibly massive stars and the earliest quasars acted like a cosmic ultraviolet laser, blasting through the neutral hydrogen and stripping electrons from their atoms. This process of ionization swept across the universe, turning the opaque sea of gas into a transparent medium, one that would allow light from all future stars and galaxies to travel freely across billions of light years. We are now using our most powerful telescopes as time machines to try and witness this cosmic dawn. Observatories like the James Webb Space Telescope are peering back to this pivotal era, searching for the faint, redshifted glow of the very first stellar nurseries. Understanding reionization is like finding the missing chapter in the universe's biography, the tumultuous adolescent years when it evolved from a simple, dark void into a complex, structured, and luminous realm. What were those first stars like, and how did their explosive death seed the universe with the heavy elements necessary for planets and life? This cosmic renaissance marks the moment the universe woke up, and we are just beginning to read its first, faint memories of light. Beyond the brilliant points of individual galaxies lies a faint, all-encompassing glow. This is the cosmic infrared background, a diffuse light that fills the entire sky, a whisper of every star that has ever shined. It is the accumulated energy of stellar nucleosynthesis, the universe's total fossil light, stretched into the infrared by the relentless expansion of space. To measure this background is to take a census of cosmic history, to count every star that ever burned across all of time. This is not the light from one galaxy or one era, but the sum total of all starlight ever produced, a collective memory of stellar birth and death. Isolating this faint signal from the brilliant foregrounds of our own solar system and galaxy is a monumental technical challenge, like trying to hear a single soft voice in a roaring stadium. Yet once detected, this background becomes a powerful tool. It tells us that the early universe was far more productive than we once thought. Galaxies in their infancy underwent ferocious bursts of star formation, creating stellar populations at a rate that puts our present-day, sedate cosmos to shame. These early episodes of intense creation are often hidden from our direct view. Their original ultraviolet light stretched so far into the infrared by cosmic expansion that it blends into this universal background hum. By analyzing the specific patterns in this fossil light, astronomers can peer back to these hidden chapters, constraining how galaxies assembled their stars over billions of years. This cumulative glow reveals the universe's reproductive history, its most fertile periods, and its gradual slowing down. It acts as a check on our theories of galaxy evolution, confirming that the grand tapestry of lights we see today was woven in a frenzied and brilliant youth. What other secrets about the universe's most prolific eras are still encoded in this ancient, all-pervasive light? A testament to the trillions upon trillions of stellar lives that have illuminated the cosmic story. That faint, all-encompassing glow of cosmic history is punctuated by flashes of pure mystery. In 2007, astronomers sifting through archived data from a radio telescope found something no one was looking for: a blast of radio waves so brief it lasted only a few milliseconds, yet so powerful it released more energy than our sun emits in 80 years. This was the first detected fast radio burst, a cosmic scream from a distant galaxy that arrived and vanished in the blink of an eye. Since that chance discovery, hundreds more of these enigmatic signals have been detected, each one a fleeting, brilliant flash in the radio sky. They arrive from all directions, implying their sources are scattered across the universe, some originating billions of light-years away. The sheer intensity is baffling. How can any natural process generate such staggering power and focus it into a pulse shorter than a snap of your fingers? The mystery deepens with their behavior. Most fast radio bursts are one-off events, a single, spectacular shout into the dark. But a few precious sources repeat, sending out random, unpredictable flashes over days or years, ruling out any explanation that involves the total destruction of the source. This repetition is a vital clue, pointing toward objects that can survive these tremendous releases of energy. The current best candidates are magnetars, a type of neutron star with a magnetic field so powerful it could erase a credit card from half the distance to the moon. A starquake on such an object, a sudden cracking of its rigid crust, could theoretically unleash a firestorm of radio waves in an instant. Yet even this extreme explanation is stretched to its limits by the most energetic bursts we have recorded. This has led scientists to consider even more exotic possibilities, like the snapping of cosmic strings, hypothetical defects in the fabric of spacetime left over from the Big Bang. While the possibility of an artificial origin, some unfathomable technology, is often entertained in popular culture, it remains the least likely explanation in the scientific community, a hypothesis of last resort when all natural avenues are exhausted. Beyond their mysterious origins, these bursts have become unexpected tools for cosmic cartography. As a fast radio burst travels across millions of light-years, its different radio frequencies are slowed by the thin plasma between galaxies. By measuring this delay, astronomers can calculate the total amount of invisible, ionized gas the signal has passed through. This allows them to weigh the universe's missing baryonic matter, the ordinary atoms that are predicted to exist but have evaded our telescopes, hidden in the vast voids between galaxies. Each mysterious flash is not just a puzzle, it is a probe, illuminating the dark, diffuse material that forms the cosmic web itself. What other invisible structures of the universe will these random, brilliant messengers reveal as we build new telescopes designed to catch them in the act? Our most precise cosmic recipes contain a single, baffling error. The first few minutes after the Big Bang were a searingly hot forge, a period known as Big Bang nucleosynthesis, where the universe cooked up its first atomic nuclei. Our models for this primordial kitchen are spectacularly successful, predicting with stunning accuracy the observed cosmic abundances of the lightest elements, hydrogen and helium. Yet for one particular ingredient, the calculations are stubbornly wrong. The models predict that a specific, small amount of a lithium isotope, lithium-7, should have been created. When astronomers measure the oldest stars in our galaxy, which preserve the chemical fingerprint of that early cosmos, they find only about 1/3 of the predicted lithium. This is the cosmic lithium problem, a quiet but persistent discrepancy that has puzzled cosmologists for decades. How can our understanding be so right for hydrogen and helium, and yet so seemingly wrong for lithium? The solution is not a simple measurement error. The oldest, most metal-poor stars show this lithium deficit consistently, pointing to a genuine flaw in our picture of the universe's first moments. One possibility is that our knowledge of the nuclear physics itself is incomplete. Perhaps there were unknown nuclear reaction pathways in that primordial soup, reactions that destroyed lithium as quickly as it formed or converted it into other elements. Another intriguing idea points to the involvement of exotic, unknown particles. Certain theoretical particles, like those suggested by some dark matter models, could have been present in the early universe, interacting with the nuclear broth and subtly altering the final yield. Alternatively, the answer may not lie in the beginning, but in the aftermath. Maybe the primordial lithium was produced correctly, but then it was systematically destroyed over billions of years inside the very stars we use as cosmic probes. The turbulent interiors of stars could have dragged the lithium down to hotter regions where it would be fused into heavier elements, leaving the stellar atmospheres we observe depleted. This puzzle is a powerful reminder that even our most celebrated and successful scientific models are not perfect. They are maps of reality, and the lithium problem is like a small, uncharted island on that map, indicating a territory we do not yet understand. It is a clue, a whisper from the universe's first 3 minutes, suggesting that a fundamental piece of the cosmic story is still missing from our textbooks. What other subtle inconsistencies in our data are quietly pointing toward a deeper, more complete theory of everything? The serene spiral of a galaxy, with its elegant arms sweeping through the void, presents a picture of graceful order. Yet this cosmic pinwheel hides a profound rotational mystery. According to the well-tested laws of gravity, stars orbiting a galactic center should behave just like planets in our solar system. Mercury, close to the Sun, swings around at a blistering speed, while distant, icy Neptune plods along in a slow, stately orbit. The pull of gravity weakens with distance, so objects farther from the central mass should move more slowly. This same logic should apply to galaxies. The bright central bulge contains most of the visible mass, so stars in the outer reaches, far from this luminous core, should be creeping along. In the 1970s, astronomer Vera Rubin set out to measure this expected slowdown. With meticulous care, she and her colleague Kent Ford analyzed the light from stars at different distances across several spiral galaxies. They measured the subtle Doppler shifts in the starlight, which revealed how fast those stars were orbiting. The data they collected was clear and utterly baffling. The stars in the outer regions were not moving slowly at all. Their orbital speeds remained high, nearly constant from the inner galaxy all the way out to the faint, distant edges. It was as if the entire rotation curve of the galaxy was flat, defying the fundamental predictions of gravity based on the stars and gas we could see. The only conceivable explanation was that galaxies were not what they appeared to be. They were not just islands of stars, but were instead embedded within enormous, massive spheres of something invisible. This unseen material, this dark matter, had to form a vast halo around each galaxy, its gravitational pull reaching out to grip the outer stars and whip them around at unexpectedly high speeds. The visible galaxy we admire in photographs is merely the bright tip of a much larger, much more massive iceberg, with the dominant component remaining completely hidden from our telescopes. This discovery provided the most direct and compelling evidence that dark matter was not just a theoretical idea, but a physical reality shaping the dynamics of every galaxy. It forced a complete reimagining of cosmic structure. What would a galaxy truly look like if our eyes could perceive this invisible halo? The brilliant spiral arms would be dwarfed by a colossal, ghostly sphere of dark matter, a formless cloud whose gravity is the true master of the celestial dance. This rotational anomaly remains one of the most robust clues in the ongoing quest to identify what this mysterious substance actually is. These individual cosmic puzzles, from galactic rotation to primordial lithium, were not isolated mysteries. They were separate pieces of a much larger picture, waiting for a unifying vision. That vision arrived with the establishment of the Lambda cold dark matter model, often called the Concordance model of cosmology. This is not merely a single theory, but a complete and consistent framework that weaves every major cosmic observation into a single, coherent narrative. It is the standard model for the entire universe, a story that begins with a burst of inflationary expansion and charts the evolution of a cosmos dominated by dark energy and dark matter. The true power of this model lies in its ability to satisfy completely independent lines of inquiry. The precise pattern of the cosmic microwave background, the vast sponge-like structure of the cosmic web, the primordial abundances of hydrogen and helium, and the accelerating expansion revealed by distant supernova, all of these different messengers from different eras point to the same exact set of cosmic ingredients. It is as if four separate witnesses to a historical event, each with their own perspective, told a story with no contradictions. This remarkable convergence gives us a profound confidence that the broad strokes of our cosmic history are correct. We have a recipe for the universe, and it works. We can take the measured amounts of ordinary matter, and dark energy, feed them into supercomputer simulations, and watch a virtual universe evolve that looks almost identical to the one we see through our telescopes. This model represents one of humanity's greatest intellectual triumphs, a collective achievement that stitches together the physics of the unimaginably small with the history of the impossibly large. It provides us with a reliable timeline from the first fraction of a second to the present day, a 14 billion-year epoch, yet for all its success, the model is humbling. It tells us that 95% of the universe is made of dark, unknown components. We have a beautifully detailed map of cosmic evolution, but we still do not know the true nature of the territory's two most dominant features. How does it feel to possess such a complete story of cosmic origins, while simultaneously knowing that the greatest chapters of discovery, those that will explain the dark sector, are still waiting to be written? This framework does not mark an end, but a magnificent beginning, a stable foundation from which we can finally ask the universe its deepest questions. This entire journey of cosmic discovery began with a simple assumption that we occupied a central, privileged place in creation. Each of these 30 events systematically dismantled that comforting illusion, replacing it with a far grander and more humbling reality. We have moved from a universe centered on our world to one where we are adrift in a vast ocean of galaxies, our very existence made possible by ancient stellar explosions and governed by invisible forces. The true power of this transformation lies not in any single discovery, but in their profound interconnectedness. The quantum fluctuations of inflation seeded the galaxies whose rotation revealed dark matter, whose gravitational pull was then overcome by dark energy. The death of massive stars forged the elements for life and left behind pulsars that tested relativity, while their explosions as gamma-ray bursts illuminated the violent nature of cosmic evolution. Science rarely proceeds in straight lines. Instead, it is a self-correcting conversation with the cosmos, where each answered question reveals a deeper, more fundamental layer of mystery. The initial puzzle of the universe's expansion led to the mystery of the Big Bang, which led to the enigma of dark matter, which in turn unveiled the shocking presence of dark energy. We stand today on a foundation built from centuries of collective curiosity, a pyramid of understanding whose peak stretches higher with every generation. Our place in this cosmos is no longer one of assumed significance, but of earned insight. We are the universe awakening to itself, a fleeting consciousness born from stardust, now capable of looking back across 14 billion years and tracing the contours of its own origins. This perspective is both liberating and daunting, for it reveals that we are participants in an ongoing story whose final chapters are not yet written. The remaining mysteries, from the identity of dark matter to the ultimate fate of space itself, are not failures of understanding but invitations. They are the next set of cosmic clues, waiting for the curious minds who will use them to once again reshape our conception of all that is. These 30 cosmic events are not just a collection of facts, but a chronicle of human curiosity itself. Each discovery, from the Big Bang's echo to the first image of a black hole's shadow, represents a moment where our species peered deeper into the dark and came back with a new piece of the cosmic puzzle. They show us that progress is not a straight path, but a series of revolutions, often born from questioning the most deeply held assumptions and embracing the most unexpected results. Every time we built a better telescope or designed a more sensitive detector, the universe revealed a new layer of its profound and beautiful strangeness. This journey reminds us that the cosmos is not just stranger than we imagine, but as the saying goes, stranger than we can imagine. Our tools will continue to evolve, and with them, our reality will be reshaped once more. The next paradigm-shifting discovery is out there, waiting in the data or in the dark sky for the next curious mind to find it. We would love to hear from you which of these cosmic events most profoundly changed your view of the universe. Share your thoughts in the comments below, and if you are eager for more journeys to the edges of understanding, subscribe to continue exploring.